Okay, next we will discuss drift current. How we can define it. The electric current due to the presence of electric field is called drift current. As we already derived a relation for the drift velocity, which is Vd, which is equal to mu into tau, where tau is the relaxation time and mu is the mobility, which is equal to QE over m. In this case, we consider a general expression. We didn't consider electron or hole. Okay. Now suppose this is the mobility. Now suppose we have a piece of semiconductor. Okay. We connect it to an external voltage source. Here we have the positive charge, positive terminal, and here we have the negative terminal, and this is the external voltage. The length of the semiconductor rod is L. And we know that there is an electric field developed inside this semiconductor rod. Its direction is from positive to negative terminal. So its direction is this one. This is the direction of electric field, which is given by E is equal to V over L. This is, let's say, equation number 1. Now inside the semiconductor we have free electrons, which are denoted by dot. I will just consider one electron. Okay, there are many free electrons, and we have holes also. The charge of electron, this is electron. Okay, and electron charge is minus q, where q is 1.6 into 10 raised to the power minus 19 coulomb. And we have free holes, which are denoted by this empty circuit. The electrons are denoted by these dots, and these are denoted by, holes are denoted by these circles H. And the hole has a charge Q, and Q is value this one. Now the force, since there is an electric field, so it means that there is a force, and the force on electron is given by minus Q into E. This is, let's say, equation number 2. But this force will be in opposite direction to the electric field. If electric field is this one, then the force direction is this one. Now the force, this is force on electron. Okay, force on electron. Similarly, force on hole will be F. I will call it F. Okay, and it is equal to QE, because holes is a positive charge, and it is in the direction of electric field. This is the force on hole. Now the current due to the flow of electrons is in a direction opposite to the flow of electron, or the current due to electron is in a direction which is opposite to the direction of flow of electron, because we know that the conventional current direction is in opposite direction to the electron flow. So this is the direction of current due to electron, and I call it Jn. N is for electron, which we call drift current, Jn drift, because it's because of electric field. And the drift current density, and similarly the whole current, the current density of hole, which is denoted by, this is force, and its direction is this one, Jp, P for holes. Okay, drift, which is in the same direction as the flow of hole, because the conventional current is in a direction to the flow of positive charge. Now the total drift current that is flowing through this semiconductor is denoted by JT or J drift, which is equal to the total drift current, which is equal to the drift current due to electrons, Jn drift. It is a vector quantity, so I will put vector here, and plus current due to flow of holes, Jp drift. In general, current density is given by, we define the current density as rho v into v, where rho v is the volume charge density and v is the velocity. This v is the velocity with which these volume charge move. Now we will check whether this equation is true or not. This is the current density, which is, and this is volume charge density times velocity. Current density has a value which is current per unit area, A over meter square, ampere per meter square. Its unit is ampere per meter square. And charge density is charge per unit volume, which is meter cube, times velocity is meter per second. So ampere per meter square is equal to coulombs. Meter cancel with this, so this 3 will become 2. So coulombs per second, I can write it as like this, and then we have meter square. So ampere per meter square is equal to ampere per meter square. So the unit are same, so it means that this equation is valid. Now the drift current due to electron, J n drift, is equal to charge density is volume charge density is minus q into n times velocity is v drift. Now here the negative sign show that the drift current is in a direction which is opposite to the velocity of electron, and v and d is the drift velocity, where v and d, this is for the electron, so v and d is for the electron, is the drift velocity of electron, which is given by v and d. We already defined vd as this one, so it's mu n into e, but there is a negative sign for the electron because mu is QE divided by m steric. Then charge is negative for electron, so we have minus mu, which is minus QE over m steric. That's why we have a negative sign here. And if we put this value in above equation, we get J n drift. The current density, drift current due to electron is mu n, and we have q n e. So this is a vector quantity. I will put vector sign here. And this is equation. Let's suppose this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. Using 7 in equation, okay, this is equation number 7. Now similarly, for holes, the drift current is, which we represent by Jp drift, which is equal to volume charge density, which is QP. Okay, and we have drift velocity of hole, VPD. Now drift velocity of hole is mu e. So this is a vector quantity. I will put vector sign here because mu is QE divided by m steering. For hole we have charge positive, so it's just a positive. Now using this value above, we get JP drift, which is mu e QP into VPD. Let's say this is equation number 8. Using equation 7 and 8, using equation 7 and 8 in equation 4, we get the total drift current J drift, which is equal to mu n q n e plus mu p. Yeah, this is mu p. This is for the electron hole. Mu p e qp into qp. Yeah. Now q is common in both this expression, and e is common. So we have q into e, and here we left with n into mu n plus p into mu p, which is total drift current JD drift. This is the expression for the drift current in a semiconductor. We can write this in Ohm's law. We can write this in terms of Ohm's law like this. J drift will be equal to, this is a vector quantity, sorry, I'm forgetting the symbol of vector. J drift is equal to sigma E, where sigma is Q times n mu n plus p mu p, and it's called conductivity of the piece of semiconductor. So we have these two relation. This is the drift current and this is the drift current in terms of Ohm's law. In the next video we will go to the diffusion current. Thank you.